SwayamPrabha. Digital India. Educated India.
In this lecture, we will continue our discussion on introductory aspects of high temperature Inviscid equilibrium flow. We would discuss about heat of reaction and heat of formation, followed by gas mixture enthalpy calculation, and then finally, we will look at thermodynamic properties of high temperature equilibrium chemically reacting air using Mollier chart and some polynomial correlations. This is where we ended our discussion last time. If you recall, we were trying to define the heat of formation, and earlier to that we had learnt about the heat of reaction. From the heat of reaction, we qualified it to heat of formation for a special case where there is formation of a single chemical species from its elements at standard conditions. And then we discussed about what we mean by standard conditions, what we mean by stable elements at standard conditions, and so on. Trying to extend it, let us recapitulate heat of reaction once more. When we have a chemical reaction under equilibrium, we consider the reactants to be at a temperature of T ref, a reference temperature, and we would like to maintain this reference temperature as the chemical reaction progresses, which means we may have to add or subtract heat to the chemical reaction in order to maintain it under isothermal conditions. When we consider this reference temperature, at this temperature, first of all we sum up the total enthalpy of the reactants. If there are different species, then we call each species enthalpy level as H I if it is on a per mole basis, and then we try to sum them up. Let the chemical reaction progress under constant pressure. So, in addition to holding the temperature at T ref, we also impose a condition that the reaction should progress under constant pressure conditions. There is a reason behind it, we will soon see. If you recall from your memory, you will not be surprised. Finally, we have to extract or add based on whether it is an exothermic reaction or an endothermic one, enough heat from or to the system, so that the products are also brought to the T reference temperature. In fact, all the way as the chemical reaction progresses, this T reference temperature has to be held constant through a continuous heat exchange if required. Now, the extracted or added heat from the thermodynamic system is basically the heat of reaction. This heat transfer ensures that the products are maintained at a constant temperature, and if you are further holding a constant pressure during the process, what happens is that the heat exchange with the gas or the medium essentially leads to its enthalpy change. Therefore, heat transfer is equal to change in enthalpy. The heat of reaction at the reference temperature is indicated by this relation delta H R, R for reaction. Later on you will see we will use a subscript F for formation, and this is the temperature, that is the reference one, and delta H R is basically the enthalpy of the products minus the enthalpy of reactants, all held at the T reference temperature. Finally, that can be indicated like this as a summation, where we have negative or positive values for reactants and products respectively, where the nu indicates the stoichiometric mole numbers and the H values are for the different species. The species here is AI and all maintained at temperature T ref. These delta HR T ref values can be calculated from tables like the Janaf tables, which are very popular, or by using statistical thermodynamics or statistical mechanics tools. So, this was a brief recap. One more important information which we would like to once more emphasize on is that when the heat of reaction is negative, heat is evolved out of the chemical reaction and it is an exothermic process. Therefore, you have to remove heat from the gas in order to maintain it at the reference temperature, while heat of reaction being positive means that heat must be absorbed by the gas because it is an endothermic process. So, if you do not allow that heat transfer, then it will not be able to maintain the reference temperature, it will drop below that. In order to ensure that it does not happen, you provide heat to the gas. So, exothermic and endothermic reactions therefore have the respective signs, or the negative or positive signs as they may apply based on these definitions, which are very, very important. Let us next discuss about heat of formation. We were talking about standard condition in the context of heat of formation. Once again we mentioned that, and remember about the temperature that we were talking about. At these kind of temperatures, obviously, if you are talking about formation of water from its stable elements, then the elements respectively are molecular hydrogen and molecular oxygen, because those are the stable forms of those elements under such conditions, and they react with the respective stoichiometric mole numbers that are indicated here to form water. And if you were to express it in terms of standard heat of formation of water, then this is the expression that you would need to follow. So, the delta H f for water at T equal to 298.16 Kelvin will be expressed in terms of enthalpy of products minus enthalpy of reactants at the same temperature, where you have to be careful about using the stoichiometric mole numbers carefully, 1 here, while half here in the case of molecular oxygen. When the reference temperature is considered to be absolute 0, then the same expression would have to be written for absolute 0 temperature set as the reference one. Interestingly, the sensible enthalpy under such conditions will go to 0. And what is the consequence? The enthalpy of any species at absolute 0 will be equal to the 0 point energy by definition, which basically means that this equation could be reinterpreted in a form like this. It comes from this particular form for H I, which we had discussed earlier. That means, straight away the H terms can be replaced by their E naught terms, because we have reduced the reference temperature to absolute 0. We want to further establish another fact, that in a chemical reaction the net change in 0 point energy, which is the 0 point energy of all products minus 0 point energy of all reactants, can be equated with the heat of formation of the products subtracted from heat of formation of the reactants. We will take a water gas reaction, water reacting with carbon monoxide producing carbon dioxide and H2, and we start by introducing the change in 0 point energy for the reaction. By definition, the products have positive sign, the reactants negative sign for all the constituent elements. We write down the chemical reactions which help to calculate the heat of formation. Remember that for the heat of formation, each one of the species have to be formed from its stable elements. So, starting from water to carbon monoxide, carbon dioxide, we have to for each one of those species write down the relevant chemical reactions. It so happens that for water we had already seen how the equation looks like, that means how the heat of formation is worked out. For carbon monoxide and carbon dioxide, this is how it is done. Again, products with positive sign and reactants with negative sign, with the stoichiometric mole numbers to be associated with 0 point energy of each species on a per mole basis. That is how the calculations take place. Only for molecular hydrogen there is an exception, the delta HF happens to be 0. Add the third and fourth equations and subtract the sum of the first and second equation, and then you will end up getting a form like this. So, when you write that form, you will find that many of these terms cancel out. So, you can associate these two terms on one side and associate these three on the other, which would go out because of the cancellation, and finally, you are able to establish this, which is nothing but the delta E naught, the change in E naught between products and reactants. So, we could establish what we set out to show, that is delta E naught on one hand is the difference between the heat of formation of products and reactants, and at the same time it is the difference between the 0 point energy of the products and reactants. And there seems to be a kind of 1-to-1 correspondence in between the terms that form the two equations for delta E naught. Incidentally, this is not a special result, it is a general result and it holds good for reactions in general. You can try out other reactions too and you will find the same fact coming back over and over again. We recall the expression for the gas mixture enthalpy per unit mass of the mixture, where we would like to introduce the latest finding. How would you like to introduce it? Beginning with this definition, that H, which is a per mass calculation, can be expressed in terms of the product of mole mass ratio and the enthalpy for each species, and then you split the enthalpy into sensible part and the 0 point energy part, and you can say that this can be kept as it is and can be obtained, for example, from statistical thermodynamics principles, while the other part, the 0 point energy, can be expressed in terms of delta HF at absolute 0. So, this will be called as an effective 0 point energy of the mixture, which is expressed in terms of delta HF at t equal to 0 for each and every species, and incidentally this can be obtained from tables, which is a big convenience. When we express the above relations per unit mass, then we have to just make some changes. We have to bring in the small c I, the mass fraction, into h I, the lowercase h, which is on a per mass basis, again split it into the sensible part and the effective 0 point energy and express. Recall that we have shown earlier that how H minus E naught for every species can be expressed using statistical thermodynamics. We had an expression which explicitly showed that form in the previous lecture. you can revise it once more if you want. Similar would be the case for the small h minus small e 0 for each species when you convert it to per mass basis, and therefore, there would be the specific gas constant coming into the different energy modes. The eta I and C I of course, come from the equilibrium composition of the equilibrium reacting gas mixture. Therefore, we are trying to put things together. Earlier we had learnt about thermodynamic properties of single species, then we learnt about composition of an equilibrium gas mixture, and now we are trying to build a kind of a framework where we can calculate the thermodynamic properties of an equilibrium gas mixture. So, that is the target we are fulfilling currently. With what we derived for a general gas mixture, we can also look at air in specific, because that is the most commonly handled medium when we are studying aerodynamics. So, here we would look in particular into the properties of high temperature equilibrium chemically reacting air. Obviously, a high temperature air forms a gas mixture comprising of several species. We have been emphasizing it over several lectures, and when this mixture is in equilibrium, it satisfies the requirement of thermodynamic equilibrium as well as chemical equilibrium. The thermodynamic equilibrium has to mean that there is a Boltzmann distribution existing in the gas mixture, where the energy is quantized over different levels. The chemical equilibrium means the chemical composition of high temperature air satisfies the chemical equilibrium calculations which we have performed using the equilibrium constants. These constants could be derived from classical thermodynamics as well as statistical thermodynamics. And in an equilibrium high temperature airflow, the thermodynamic and chemical equilibrium has to be satisfied locally. What we mean by locally is that point to point the thermodynamic properties are going to vary, and therefore, with all the variations that occur as we move along with the flow, locally at every point we need to make sure that both the thermodynamic and chemical equilibrium aspects are fulfilled. In order to solve high temperature equilibrium airflow, two thermodynamic state variables have to be chosen. Again, they have to be expressed in terms of two other state variables. For example, if we choose to take two state variables, let us say temperature and pressure, which are most often used, then you might decide to express temperature and pressure both in terms of density and enthalpy. That is how 2 plus 2 4 state variables get involved when we talk about high temperature equilibrium airflow. Now, these variations can be expressed in the form of functions. So, how can we make these functional forms made available? They can be obtained in various ways. They may be obtained through statistical thermodynamics or tables of thermodynamic properties of high temperature air, graphical plots like Mollier diagrams, or polynomial correlations based on high temperature air table data. There are different ways. Tables, of course, we have been talking about JANAF for quite some time. So, there are different sources from which information may be sought. It is a good time to have a look at Mollier chart for high temperature equilibrium air. We have enthalpy and entropy, enthalpy along the y axis, entropy along the x axis, and we are looking at behavior of high temperature air by following isotherms. So, these are isotherms, at 2000, 4000, 6000 and 8000 Kelvin respectively, and when the density changes by scaling it with respect to the density at standard conditions. So, you have a very dense situation rho by rho naught of 100, then it is 1, then it is 100th and then 1 by 10 to the power of 4. So, very low pressure, and then we see very peculiar variation of the isotherms. So, in order to explain the behavior, let us try to delve a little deeper into it. Isotherms are nearly horizontal at low temperatures. So, if you are below 2000 Kelvin, you will basically see them as horizontal lines, and under such conditions H depends only on T, it has no dependence on S basically. As you move along the S axis, you do not see a change in H for a given T. This gives a thermally perfect behavior of air, and when you go to higher temperatures, especially beyond 2000, and gradually the effects become much sharper as we go to still higher temperatures like 4000, 6000 and 8000, the effects get amplified further. What is that? The fact is that H increases rapidly with increase in S, while the T remains constant. This is typically a characteristic of chemically reacting air, where dissociation chemical reactions are taking place. For example, in air, as the temperature increases at 1 atm pressure, for example, we know the relevant temperature ranges which are important for us for dissociation of O2 and N2. So, like that, as density changes and it reduces below 1 atm, such dissociations can occur at still lower temperatures. Keeping all this in mind, let us proceed with the discussion. At high temperatures of 4000 Kelvin onwards, dissociation is significant, and if we consider 1 atm pressure, O2 has already dissociated, N2 has started dissociating, and the following facts will hold good. As density decreases further while following an isotherm, the pressure decreases and hence dissociation increases. So, if you refer to the equation of state, following an isotherm would mean temperature remains constant, and therefore, if density reduces, the pressure also reduces. At reduced pressure, the dissociation rates increase significantly, and then you have a higher concentration of atoms compared to molecules. So, concentration of atoms is increasing, molecules is decreasing. Consequently, what happens to the 0 point energy contributions is what is very important. When you have two atoms of a molecule having a combined 0 point energy that is higher than 0 point energy of the molecule, then having more atoms in the population would mean that more of the energy goes into the 0 point energy of the atoms. Therefore, as pressure decreases, with increase in S at constant value, the effective 0 point energy of the mixture increases. Since the H represented in the Mollier chart includes the effective 0 point energy, therefore, H would significantly increase even though you are at constant T the moment you start reducing the density. Again, if you just recall from a calorically perfect gas, the entropy change equation kind of helps you to understand what is going on. If you assume an isothermal process, that is what happens when you follow an isotherm, you find that this contributes nothing. You are further reducing the pressure because you are going to lower densities, and under isothermal condition that means lower pressures, which would mean that minus R log P 2 by P 1 will give you a positive contribution, which means entropy is increasing. This is exactly the trend which is seen over here, and therefore, in the case of a equilibrium gas mixture also, what happens for a single species considering a calorically perfect gas in principle kind of extends in this case too. We saw the graphical plot of high temperature air properties through the molecular the Mollier diagram or chart in the last few slides. Before we close this lecture, we would also like to talk about some polynomial correlations. They are commonly used to obtain such high temperature air properties. The correlations are reported in a very popular report, the NASA CR 2470 by Tunhill and Mugg, which is very useful, and they have different thermodynamic variables expressed in terms of polynomial correlations, which are based on tables of data of high temperature air. For example, the enthalpy here is the specific enthalpy is expressed as a function of pressure and density, and they have a gamma H tilde term, which is expressed in terms of a large number of constituent terms with coefficients and some variables like y and x defined in terms of density and pressure, and further one more variable defined as a difference of x and y. The coefficients are all provided in the table in the reference that we quoted. Like enthalpy, you will see similar correlations available for pressure, for example, as function of rho e, and another correlation for the gamma, which we may call as gamma p tilde, and also correlations for temperature. And interestingly, these correlations compare very well when we compare it with tabulated data, which means instead of using the tables, reading of the tables, we might as well plug in these correlations into codes where we are solving high temperature equilibrium flow, where we have to incorporate the high temperature effects, and therefore, these kind of correlations could be very well suited for flow solvers. Before we finish, we would like to have a look at few of the important points here. We discussed about possible methods of obtaining the thermodynamic properties of a high temperature equilibrium gas mixture in the last two lectures, which are the first two of week 8. In particular, we discussed about how it applies to finding thermodynamic properties of high temperature air, which is going to be most important for us. With the thermodynamic properties of the gas, predominantly air for our case, we would now be in a position to calculate different flow fields involving shocks, blunt bodies, nozzles, where high temperature effects are accounted, and we consider the flow to occur under equilibrium, both thermodynamic and chemical. Those would be addressed in the next few lectures of this week. We would assume that an element of fluid moving through a non-uniform flow field obeys the same thermodynamic relations that we have obtained for a stationary system in complete thermodynamic equilibrium. And if that assumption is made and allowed, that allows us to incorporate equilibrium thermodynamic relations directly into the structure of high temperature gas dynamics, and that is the most important relevant point that we are trying to make over here. So, we have built some tools which can be plugged into high temperature gas dynamic modeling, and there the thermodynamic properties that we have obtained at high temperatures will be plugged in into the flow equations. This would be required to relate the various state variables that appear in the conservation equations, which actually would model the flow. When we shall write the governing equations for high temperature inviscid equilibrium flow, we would assume that the effects of molecular transport, namely viscosity, thermal conductivity and diffusion, are negligibly small. That is what we do when we look at it from an inviscid point of view. These are the manifestations of non-equilibrium in translational and rotational motion of the molecules. We are not modeling non-equilibrium, and therefore, these are neglected. We would keep this aside in the discussion of inviscid equilibrium high temperature gas mixture in this week's content. Non-equilibrium effects will be taken up in the next week. The assumption of complete local equilibrium implies that all molecular processes take place within the gas infinitely rapidly. That is, that the gas can adjust instantaneously to changes in its environment, and this is a very important part of the concept of equilibrium. So, the infinite speed with which the thermodynamics adapts, the chemical reactions adapt, makes it the most important, the pivotal point to ensure that we have local equilibrium from point to point in a flow field, ensuring thermodynamic as well as chemical equilibrium issues. We conclude by saying that in this lecture we discussed the heat of reaction and heat of formation and their significance in calculating the enthalpy of an equilibrium gas mixture. Like we did for enthalpy, other properties of the other thermodynamic properties of the gas mixture can also be derived based on similar principles. Thermodynamic properties of high temperature, equilibrium, chemically reacting air were studied, and the molecular chart and polynomial correlations were discussed. With this, we end this lecture. Thank you.